Okay, well, thank you very much. So thank you, Sakenta, for those kind words. And thank you, well, Shreshti and everyone else that invited me and set this up. It really is a pleasure, an honor to talk to you about continuous gravitational waves this morning. So I'm from the University of Southampton. For those of you who don't know, that's a town on the south coast of England, just over an hour by train south of London. It's one of the ports that the Titanic sailed from, so that was one of our big successes. And if you ever get the chance to visit, that would be very nice. So this is going to be very much a theory lecture on sources of continuous gravitational waves. The lectures that you'll have tomorrow and Wednesday will be more focused, as Sukanta said, on sort of data analysis aspects, but we thought it would make sense to talk about the physics of the sources first. So I hope you can all clearly see, well, I guess it's slide number 2. So what do we mean by a continuous gravitational wave? Maybe we should start by asking that question. Well, there's no sort of really hard definition of this, but I would say a continuous wave is a signal that lasts for a long time. And what do we mean by that? Well, this is the bit that's not so precise, but at least days. You may have heard, in addition to continuous waves, of transient gravitational wave signals. There's no sharp dividing line between what we mean by a transient signal and a continuous wave, but what we would generally say, and I've said it, we should normally think of at least a few days for a continuous wave, is that when a signal lasts that long, the fact that the Earth is moving becomes important in the detection process. And this is something that my colleague Carl is going to talk about in some detail tomorrow. But basically, because the Earth is spinning on its axis, then of course the actual arms of the detector rotate through a full circle once a day. And so that affects the way in which the gravitational wave projects onto your detector, and the way that happens, depends on its direction and its polarization. But more importantly, as the Earth spins on its axis and as the Earth orbits the sun, you get a Doppler correction. Now, if the Earth was just moving in a straight line forever, that would be a constant Doppler correction and it would be no big deal. But because the Earth is spinning, and it turns out you get a bigger effect because the Earth's orbiting the sun, you get a time-varying Doppler shift. And the tricky thing is that this Doppler shift is different for different directions on the sky. That's obvious, right? Because, if the Earth is traveling towards the gravitational wave source, then that source is sort of blue shifted, its frequency's increased a bit, whereas if the Earth's traveling away, it's red shifted a bit. But of course, 6 months later, that's completely reversed. So what that means is that if one wants to go looking for a continuous gravitational wave signal, and certainly one that lasts months or longer, you've really got to take this sky direction dependent Doppler modulation into account. And what that means in practice is that if one is looking at all directions in the sky, then you have to divide the sky up into lots of tiny little patches and do your Doppler modulation or demodulation separately for each little sky patch. I've not put it in these slides, but it's a fun exercise to estimate how many little sky patches you need, and consequently, what the computational cost is of doing a long all-sky search. If you put the numbers in, what you can quickly convince yourself of is that you could easily saturate all of the computing power on the planet many, many times over. You simply can't throw enough computing power at this problem to do it as you wish. So this is one of the things you should understand right from the outset with continuous gravitational wave searches, because of this, in large part because of this Doppler demodulation, they can be very computationally expensive. And that's something that Carl, I'm sure David will talk about more in their lectures. Not something we're going to concentrate on so much now, because as I said, we're going to talk about the physics of individual stars. So next slide. So what are the possible sources that we're talking about here? Well, 99% of the time when we're talking about gravitational waves, it's the first of these bullet points, and I hope you can see my mouse. I put it next to the first sort of sub point. 99% of the time, we're thinking about neutron stars and basically a spinning or oscillating neutron star. But that isn't the only thing that could produce a continuous gravitational wave. And mainly in the last few years, people have started thinking about some other things. There are at least two things connected with particle physics, both of which are somewhat speculative. The first is the idea that you can get these so-called boson clouds around black holes, and through some sort of superradiance thing, they can emit gravitational waves. And there's been a little bit of work actually looking for these sorts of signals in LIGO data. Another, also speculative thing, is this so-called dark photon, dark matter. Now, technically, this isn't a source of gravitational waves, but rather it's still something, though, that would produce a nearly monochromatic and very long-lived signal in your detector. So it's not actually a gravitational wave itself, but it's something that you would show up in a detector as if it were one. And there's even been a LIGO Virgo paper on that, and I've put the archive reference down there. Then, in my opinion, somewhat less speculatively, is the idea that maybe there are some primordial black hole binaries left over from the early universe. The idea here is that if they've got sufficiently low mass, they could be in the right frequency band for LIGO to detect as continuous wave sources. And there's been some analysis of LIGO data looking for those. So what I'm going to do in these lectures is focus entirely on the first of these, so the sort of the mainstream, the spinning and oscillating neutron stars. So it's all neutron stars for us. But you should bear in mind that that's not the only possible sort of continuous wave signal. And people are starting to take these other possible signals more seriously. So next slide. So let's now focus in our attention specifically on neutron stars. There are three main emission mechanisms that we talk about. There's the so-called mountains. So mountains is not a great word for what we really mean. What we really mean is this, that if you had a spinning neutron star, if it was perfectly axisymmetric, and if it really were just rotating steadily, you wouldn't get any gravitational waves. But if it's slightly non-axisymmetric, so it's sort of bulging out in a bit, maybe if it's rotating around the z-axis, it's sticking out more along the x-axis than the y. That's what we mean by a mountain. So really, we should call it a triaxial star. And this is probably the emission mechanism that we most often think about when talking about neutron star continuous wave emission, because it's a very simple thing and it's a very natural thing to expect to occur at some level in all neutron stars. So that's what we mean by mountains. Another thing that we talk about, but not nearly as much, is free precession. So if you take a steadily spinning object and you just kick it slightly, you perturb it slightly, you can set it into free precession. And so this is just the thing that you've almost certainly studied, in an undergraduate classical mechanics course. It's what you get if you toss a rugby ball or American football in a way that makes it sort of wobble around a bit. That will emit gravitational waves as well. So we do think about these sort of signals a bit when we look at gravitational wave data, but we don't look at them as much, because if free precession were common in pulsars, remember, pulsars are spinning neutron star, right? A lot of what we know about neutron stars comes from radio pulsars. If it were common in the radio pulsar population, then radio astronomers would see the signature of this, because basically they'd expect it to show up in the radio pulsar timing, and they don't generally see it. So we do think about that a bit, but not an awful lot. And then the last of these three categories, the so-called fluid oscillations. So this is a very rich and interesting area of study, but basically a neutron star is a self-gravitating ball of fluid, not so different, say, from the Earth or the Sun. If you've got a rotating fluid, or even a non-rotating one, but it's more interesting if you've got a rotating one, then you can get oscillations in the fluid. So whereas these mountains depend on there being a solid part to the star, like the crust, these fluid oscillations, that you just need, it's just the fluid parts really that matter most for that. The picture that I've actually put on this slide is, this is a real picture of something like a Rossby mode in the Earth's, I think it's the atmosphere, not the ocean, but they're seen in both. So it's some sort of global wave pattern that's seen in the Earth, and similar things can be seen in the sun. So it's a fairly generic feature of a self-gravitating fluid that it can undergo these sort of normal modes of oscillation, and they can emit gravitational waves. There are many different sorts of oscillations, but maybe you've heard of something called the R mode. I'll talk about that later. That's particularly famous and particularly important sort of oscillation that you could have in a rotating neutron star. Okay, next slide. So what I'm going to do before talking more about the physics of these emission mechanisms is say a little bit about the way in which when we analyze gravitational wave data, we talk about different sorts of search. And I'm going to talk about three different things: targeted searches, directed searches, and all-sky searches. So the distinction now isn't to do with the emission mechanism, it's to do with how much electromagnetic information we have in advance when we go looking. And the reason I'm going to talk about these is that one of the main things I want to do in this lecture is talk about some energy-based estimates for how strong these signals might be. And the argument basically works differently depending on these different sorts of searches. So the simplest sort of continuous wave gravitational search you can do is one of these so-called targeted searches. The picture that you can see here is of the Crab Nebula. So there's a pulsar, the Crab pulsar, sitting in there somewhere. It spins at about 30 times a second. If you want to go looking for gravitational waves from the Crab, you know exactly which bit of the sky to look at. So you don't have to waste lots of computational power on Doppler demodulation. It's just basically one fixed sky location that you know. And if you think it's a mountain that's emitting the gravitational waves, you even know the frequency that it's coming out, it would be at 60 hertz, at twice the spin frequency. So it's the simplest sort of gravitational wave search you can do, because you know so much, you know where it is, and for mountains at least, you know what the frequency is. So sometimes people call these single template searches. So it's single template in the sense that you don't have to search over a big bank of templates to go looking for the signal. Can I just check, just in case something's going right? You can hear me, right?
Yeah, we can hear you, yes.
Okay, that's great. Thanks, you can. So, okay, so next slide. The next most sort of difficult search or computationally expensive search to do are these so-called directed searches. So now we're thinking that we've got some relatively small patch in the sky that we're interested in. So on the left, this is a picture of a supernova remnant. It's Cassay, in fact. There's a glowing hotspot within that remnant that astronomers think probably, not definitely, but probably is, well, there's a very good chance it really is a neutron star. But nobody's ever seen any pulsations from it, so we don't know that for sure. We don't know how fast it's spinning, but we know where it is. Another small patch of the sky that we might be interested in is a globular cluster. So globular clusters are these sort of large collectors of stars, sort of almost like mini galaxies that orbit around the Milky Way. They're quite good places to go looking for rapidly spinning neutron stars, because we know that there are lots of pulsars in them that we already know about, and they're quite good sites for having neutron stars in binaries where they may get spun up to high spin frequencies. And the important point here is that they're small sky patches. So you might, again, not have to worry about searching over multiple sky patches. One sky template would do. And then another thing that people have gone looking for in one of these so-called directed searches is looking at just a small bit of solid angle of the galactic center. So that's not exactly a point, but it's still quite a small patch of the sky. So in all these cases, in these directed searches, you've got a good idea of where to look, but because we're not looking for a known spinning pulsar, you don't know what frequency to look at. So you've still got to search over lots of different frequencies and the ways in which that frequency might be evolving. Because you don't know, it's the star spinning down really, really fast, is the frequency decreasing rapidly, or is it decreasing slowly? So they're still computationally expensive. but at least you know what sky patch to look at. Then the third class are these so-called all-sky searches. These are the most difficult in terms of computational expense of all. Basically, this is where you don't know anything. You're just looking over the whole sky at at all the frequencies that you think you've got a shot at finding something out with LIGO or Virgo or whatever. So they're extremely computationally expensive. And that remark I made at the beginning about easily saturating the computational power of the whole planet, that certainly applies for these sorts of searches. This is a screenshot of the Einstein at Home project, which is a volunteer computing project that our Albert Einstein Institute colleagues in Germany set up. So those are very computationally expensive. So those are the different classes of search. So let's get to our sort of main task, which is thinking more about neutron stars themselves. So the interesting thing, the difficult thing when thinking about continuous wave sources is that neutron stars themselves are extremely complicated and poorly understood objects, in large part because they involve high density nuclear physics. This picture that I've got at the bottom right here, this is a famous sort of cartoon diagram of the so-called QCD phase diagram. The horizontal axis is chemical potential. You can think of that essentially as a density. The vertical axis is temperature. And the idea is that each point in this, there'll be some particular state of matter, which in principle, if people that studied QCD could solve everything completely, they'd know what all these different phases are, but they don't know completely. So the basic idea is that at relatively low density and temperature, you've got fairly familiar hadronic matter, the sort of stuff that we're made from. At the top right, you'll have a quark-gluon plasma. More relevant for neutron stars, though, is that if one keeps the temperature low, but make the density high enough, you go into this so-called CFL phase. That stands for color-flavored locks. The idea here is that your quarks aren't locked up in separate hadrons like neutrons or protons or whatever. You've got like a soup of them, and they form some sort of superconducting is not quite the right word, but some sort of QCD analog of a superconductor. And so neutron star, and by the way, the sort of regime that's probed in particle physics in, say, the Large Hadron Collider is relatively low density but high temperature, whereas neutron stars in this sort of plot will be low temperature but quite high density. So neutron stars sit somewhere around here. We don't know if they move over into these exotic phases or not. Maybe they're just completely hadronic, made of relatively familiar matter. Maybe they've got high density cores that involve one of these less understood phases. And I hope they do, right? Because that would make life more interesting. But no one really knows that for sure. So that's the QCD phase diagram. And the point is, because these densities are high, the behavior of matter isn't well understood. And this is why we often say that by studying neutron stars, and by studying gravitational wave emission from neutron stars, we stand to learn about the high density nature of matter in a way that you can't learn about it with, say, the LHC. There are various aspects of this nuclear physics picture that are particularly relevant for neutron stars, and I've listed some of them on this slide here. So one of the things that matters, and probably the zeroth order thing in terms of importance, most important, is the overall pressure density relation. This is something that people often call the equation of state. Is it soft or is it hard? So this is something that in terms of gravitational waves from binary neutron star systems, people have relatively recently realized it's important because finite size effects and tidal deformability can leave some small imprint on the binary signal. But basically what I mean by soft versus hard here, if you don't know already, is so soft means that the pressure density relation is such that for a given mass star, it would be sort of small and dense. The matter is easily compressed. That would be a star built from a soft equation of state, whereas a hard equation of state means that it's difficult to compress the matter. So for a star of a given mass, it would have a large radius. So maybe if you had a 1.4 solar mass neutron star, if the true equation of state is soft, maybe it would have a radius of 9 kilometers. If the actual equation of state is hard, then maybe it would have a radius of 13 kilometers. As I say, people are beginning to probe that with binary neutron star observations, but it's something that should show up as an important thing in gravitational waves from individual neutron stars. And that affects various other things. Another thing from nuclear physics that we'd be interested in is the crust of the neutron star. There's a picture in the bottom left of like a cutaway cartoon of a neutron star. There's a question mark at the middle indicating the fact that, at high densities, we don't know really what's going on. But as the density gets lower, we've got a better and better handle. So this whole thing is a radius about 10 kilometers. The outer kilometer or so will be a solid crust. We're pretty confident of that. What we're less sure about, though, is the exact thickness of the crust. And one of the things that's important for us, because it's important for mountains, is how strong that crust is. And by strong, I mean, what's its shear modulus? How difficult is it to bend? And what's its breaking strain? How much can you bend it before it cracks or snaps or, fails in some sort of plastic way? In principle, these are things that could be computed from the equation of state, but it's difficult to do. Another thing that's relevant from the nuclear physics side, some other microphysical things, in particular the thermal and electrical conductivities and how they relate to cooling mechanisms. Some of the ways in which, pretty well all of the ways in which you can get continuous waves from neutron stars, they care either a bit or a lot about how the magnetic field is arranged in the star or how hot the star is. And so all of these so-called transport properties, the thermal and electrical conductivities, are important. And also the other transport properties to do with fluid viscosity are important. Probably not important for mountains, but they're important for fluid oscillations because they determine how much energy is dissipated as heat if you've got a fluid oscillation. And then finally, and I said things get complicated, well, they really do, because for all but the very youngest and hottest neutron stars, we think that the neutron fluid is probably a superfluid. And we think that the proton fluid, because there are protons and electrons as well inside neutron stars, we think the proton fluid is probably superconducting. So that has all sorts of implications. It tends to suppress, in some exponential way, the cooling rate and other transport properties of neutron stars, and introduces further complications. So when a superfluid rotates, it does so by forming an array of vortices. If you've got the magnetic field inside a superconductor is probably arranged into some sort of magnetic flux tube structure. So what it means is you can't just think of it as a simple, completely homogeneous fluid anymore. You've got this sort of structure on a mesoscopic scale, somewhere between the microphysical and the macroscopic, of flux tubes and vortices that could be important in understanding the dynamics. So all of these things are potentially important aspects of nuclear physics that can influence the structure and gravitational wave emission of neutron stars. So that was a sort of a long preamble. What I'm going to do in the remainder is talk about some basic formulae to do with the gravitational wave emission from neutron stars. I'll apply them in some detail to steadily spinning stars, and I'll talk about the two sorts of limits then that one can give. There are sort of theoretical energy-based limits as to how strong we might expect our gravitational wave signals to be. But then coming back to the microphysical side, we can take this nuclear physics and we can say on the basis of neutron star structure, how large we might expect these signals to be. And it's difficult to do that, and there'll be big error bars there, but we've got to try. And then I'll also talk about some fluid oscillation stuff and precession as well. So before going further, we can think about two important dimensionless numbers for neutron stars that measure just how relativistic they are. So the first is the compactness. So you're surely familiar with that. It's basically the ratio of mass to radius if you put in the appropriate factors of G's and C's, it would be dimensionless. In fact, it's one of the exercises at the end for you to do this. If you put in some typical numbers, say 1.4 solar masses and 10 kilometers, you're talking about a relativistic compactness of a few tens of percent. So this is a number that's of order 1 if you're collapsing to a black hole, and much less than 1 if you've got an object where general relativity isn't important. So it's telling us that general relativity is important for neutron stars, but 0.2 is a sufficiently small number that people very often, do use Newtonian gravity in modeling neutron stars. And then when they've sort of got their head around what's going on, upgrade and do the calculation more carefully in general relativity if they can. So that measures the importance of general relativity. We can also talk, though, if we've got a spinning neutron star, about the equatorial speed, so the speed of a point on the rotational equator. So the relevant dimensionless number here is V over C. All right, so I've put the C back in for this. If you look at the fastest known spinning pulsar, which has got a spin frequency of 716 hertz, you're talking about 15% of the speed of light. So again, it's a number that's big without being huge. So again, it's saying that, I guess you could think of this as a special relativistic effect. It's saying that relativity is again important, but you don't necessarily have to put it in your first attempt at modeling. So the fact that neither of these numbers is very close to 1 motivates people using what's called the weak field slow motion correction to Newtonian gravity to do a lot of the, not all, but a lot of the source modeling for continuous wave sources. So what we mean by that is you sort of take as your starting point Newtonian theory, and you can compute the gravitational wave emission, making standard assumptions that the fields aren't too strong and the motions aren't too fast compared with the speed of light. So the slow motion weak field approximation is basically, I'm sure it's something that even if you've not heard it called that, you'd be completely familiar with. There's a famous reference from Kip Thorne from 1980, but this is basically just talking about standard results that you'll find in all the textbooks on general relativity and gravitational waves. What we're talking about here are the so-called mass and mass current multipoles. Maybe those terms are familiar to you. I'll show you the mass. I'll show you one of these on the next slide. But basically, these are numbers or tensors, you can do it either way, that encode the mass distribution or momentum distribution in a source. And it's their time derivatives that tell you about the gravitational wave emission. So there are a set of multipoles. There's a monopole and a dipole we don't care about because they don't radiate gravitational waves, but there's a quadrupole, an octopole, and so on. And each successive multipole, its gravitational wave emission is a factor of V over C smaller than the last. And so what that means in practice, because we are talking about relatively slowly spinning systems, relatively slow motions, is that people generally talk about the quadrupole case, or in the language of spherical harmonics, if you were thinking of it that way, the L equals 2 case. And in most situations, it's the mass quadrupole, the thing that just depends where the mass is, not the current quadrupole, which is the thing that sort of cares about how it's moving, that's important. There's an exception to this, that's the R-mode oscillation that I'll talk about later. So let's talk then about the quadrupole gravitational wave emission. This next bit is standard stuff, and it would apply equally if you were modeling, say, the gravitational wave emission from a binary system. You can talk about the mass quadrupole tensor. So that's, let me just move the window a second because I can't see all of my slide. So that is the thing that you can see in equation 3. So it's, you basically take the mass density rho of the body and you weight it quadratically by the Cartesian coordinates xa, xb. In the case of a binary system, this would sort of just pick up, say, 2 point particle contributions at the locations of your 2 particles, of your 2 stars. In the case of a single neutron star and continuous wave emission, this rho would be like the smooth density, the fluid density, the total mass density of the fluid of your star. So it's given by that. I'm not going to write it down, but the current quadrupole moment, there's a tensor for that as well, and it's similar in nature, but rather than involving rho, it involves rho times the velocity. So it's not the mass per unit volume, but the momentum per unit volume that would be the relevant thing that you're integrating over. Anyway, so for the mass quadrupole, it's given by equation 3. This is a bit of a technical point, but actually the thing, that, as you may well know, that actually appears in the useful formulae is the trace-free version of this. That's the thing that I've written in equation 4. So I've basically just subtracted off the trace of this using a Kronecker delta. Then you get two formulae, the first of which is very famous indeed. I think Einstein wrote it down even. This is the formula, equation 5, for the gravitational wave luminosity. I've put units where G and C are 1 here. It depends on basically the square of the third time derivative of this trace-reduced quadrupole moment tensor. So that's something that I'm sure you're familiar with, and it's something that you can compute for a binary system quite straightforwardly to get its gravitational wave luminosity. Another famous formulae is number 6. So this is the expression for the gravitational wave field itself. The TT stands for transverse traceless gauge. I won't explain that in any detail. I hope you know about that. And that goes as the second time derivative of the quadrupole moment tensor. So let's move on and think about applying these formulae to a spinning neutron star. If we were to do that, then, well, first of all, let's think about the picture that we've got of the star. So there's just some random image of a trapezoidal body that I found on the internet here. The idea is we've got a star that's spinning about the 3-axis, the z-axis. It's not axisymmetric. And so if we call its moments of it, I'm going to change notation ever so slightly here. So now IXX, YY, and ZZ are the moments of inertia of the body about these 3 axes. They're very, very closely related to the components of the mass quadrupole tensor. Then, so it's spinning about the z-axis, the 3-axis. We're assuming it's triaxial, so maybe it's stretched along the x-axis and pushed in along the y-axis to give it this triaxial shape here. A number that you'll see in many, many of the gravitational wave papers on continuous wave sources is this so-called ellipticity. It's a dimensionless measure of how triaxial, of how non-axisymmetric your neutron star is. It's defined as IYY minus IXX. So the difference in your two moments of inertia orthogonal to the spin axis divided by IZZ, the moment of inertia along the rotation axis. If you take a star like this rotating about the z-axis and you go back to the previous slide and plug the appropriate density field into equation 3 and then just grind out the results in equation 5 and 6, then you get a well, first of all, you find that the gravitational waves come out not at the spin frequency, but at twice the spin frequency. I don't know if that seems surprising to you, but it's because it's this mass quadrupole that's generating the radiation. And it's basically the same reason why if you've got a circular binary, its dominant radiation is at twice the orbital frequency. It's essentially the same thing. The amplitude given an equation 8, well, of course, it drops off as 1 over r. It goes as the square of the spin frequency. That's come from the fact that there were 2 time derivatives in the formula, and it's proportional to epsilon. So this is in large part why we bother with this definition of ellipticity. It's a dimensionless number that measures how strong the gravitational wave signal is. The corresponding luminosity is given in this last equation. This goes as the 6th power, so a very steep power of the spin frequency, and is quadratic in the ellipticity. So what these formulae are telling us is that other things being equal, so for stars of a given, so for a star of a given ellipticity, you'll get stronger emission at high spin frequencies, not very surprising. And for a star of a given spin frequency, you get stronger emission if you have a large ellipticity. So maybe I'll take a quick look at the chat because I can see that there are a few comments in it. Let me just, in case there's anything I need to respond to now. No, that isn't. Okay, good. All right, I'll just carry on. So those formulae to bear in mind. So what I'm going to do first is talk about some energy-based upper limits that we can give on how strong gravitational wave signals might be, depending on whether or not we're talking about the targeted searches, the directed searches, or the all-sky searches that I spoke about. So this will take some time. When we finish doing that, I'll then talk about estimates of how strong the emission might be based on the actual physics of neutron stars, like the strength, the shear modulus of the crust or whatever. But let's talk about these energy-based arguments first. The idea is we're just trying to get a feel for when the gravitational wave detectors might start making detections.
Yeah, there's a question from Gurudev. Do you want to take it now or shall we keep?
I'm very happy to take a question now.
Yeah. Gurudev, please feel free to unmute yourself.
Hi, Ian. I have a question from your previous slide,
Yeah.
slide number 13. So you corrected the formula in the presence of ellipticity, but will this ellipticity increase the radiation, and will it also affect the duration of the waveform? That is not clear to me. I mean,
okay, so let me check I've understood the question. So you asked what the connection was between the ellipticity and the strength of the signal, is that right?
yes, and the duration of the signal.
Okay, well, the first part's easier to answer. So the strength of the signal, as you can see it from equation 8, really is proportional to this ellipticity, because you can see there's a factor of epsilon in equation 8. Now, the duration of the signal, it depends on exactly what's going on. But if we've just got a completely isolated, and I'm going to talk about this in detail in a moment, but basically if we've got an isolated star, then the bigger that epsilon is, you can see from equation 9, the more rapidly it emits energy, so the more rapidly its spin frequency would decrease, and so its signal wouldn't last as long. I'm actually going to talk about that in detail in a slide or two, so I guess I can get to it.
Sure, that is fine. Yeah, that's fine.
Okay. All right, is that enough to be going on with?
Yeah, thank you.
Okay, no worries. Okay, so so this is the game we're going to play now. We're going to play around precisely with these sorts of energy arguments. So before specializing too much, let's just put a few simple ideas together. What we're going to do is we're going to imagine that we've got a spinning neutron star, and it's emitting gravitational waves, but it's not losing energy in any other way. Now, lots of the neutron stars that we know are emitting lots of electromagnetic energy. They've got strong magnetic fields. So as they spin around, there's a rotating dipole, rotating magnetic dipole, and that will surely emit lots of gravitational wave energy. But let's assume that we haven't got that going on, and we've just got gravitational wave emission. So what we can then do is write down equation 10, where on the left-hand side, I've written down the time derivative of the kinetic energy. So that's how rapidly the star's losing kinetic energy. And on the right-hand side, well, according to our assumption, that must be balanced by the gravitational wave luminosity. So that's a formula from a couple of slides ago. So this is just applying the idea of energy conservation to a spinning down star whose only source of energy loss is gravitational wave emission from a mountain, a traxial thing. So this is one of the exercises that I've put at the end. One can easily integrate this to solve for the spin frequency omega as a function of time, and you get equation 11. It's basically a power law type thing. Omega naught is just the constant of integration, the spin frequency at time t equals naught, whatever that was defined to be. Maybe that's when the star was born, whatever. The actual tau, this sort of time scale, so tau is dimensionally a time scale. It's sometimes gone on which the spin frequency is decreasing. that's built out of epsilon and omega in the way that you can see in equation 12. So in fact, so to answer the question that you asked a moment ago, Gurudev, then basically the larger the epsilon is and the larger the, well, original spin frequency, the faster the star spins down. It turns out there are some neat cancellations in some of these formulae. Excuse me a moment. There are some neat cancellations, and if one makes the rather strong assumption that we're looking at a star that was born really fast and is old enough that it's spun down quite a lot, so that the time now is much bigger than its tau when it was born, then you get a neat cancellation. You get equation 13, which is telling us that its spin frequency today at time t, well, it's given by this formula here, and what you can see is that the birth spin frequency, omega naught, has dropped out. So there's some weird cancellation where if you know, one star was born spinning twice as fast as another, it then spins down more rapidly. And there's a cancellation between those two effects such that its spin frequency today is to this level of approximation independent of its birth spin frequency. It does depend on the age of the star, or, well, you know, the time now t, and it does depend on the ellipticity epsilon, but it doesn't depend on that birth spin frequency. And that will be a useful result to us in just one moment. So there's another thing that we can immediately do with energy conservation. If you look at any of the LIGO Virgo papers, continuous wave papers that have, say, look for gravitational wave and so-called spin down upper limit. And that's what I want to talk about on this slide. So the idea here is that, again, equation 14 is just energy conservation. So again, the rate of change of kinetic energy is equal to the luminosity. But whereas on the last slide, we solve this as an ordinary differential equation, you can do something simpler, but very useful with this. You can just immediately rearrange this equation in terms of epsilon, and that's what's called the spin down ellipticity, because this would be the spin down ellipticity that your star would have to have if, so let me step back a second and explain some notation here. So we started off using omega for the angular spin frequency. It's well, conventional and useful now. Let's convert to spin period p. So p is 2 pi over omega. So you can see in this next formula that the spin period p appears, but also that dot's the time derivative. So that's called the period derivative. So the rate at which the period is increasing. So for a star, if you know its spin period p, and you know it's the derivative of that p dot. So by the way, for the crab, we do know, for lots of pulsars, we know these things. Then by making this very strong assumption that the star is spinning down entirely due to gravitational waves, you get this spin down ellipticity, which we normally think of as being actually an upper limit on the actual ellipticity, because of course, surely not all of the kinetic energy that's being lost will be going into the gravitational wave channel. And so one of the exercises that I've got for you at the end is to use this formula to compute spin down ellipticities for various known pulsars, because it's quite instructive. For the Crab pulsar, if you put the numbers in, well, it's got a spin period of about 0.03 seconds. It's got a period derivative of about 4 times 10 to the minus 13 seconds per second. So that's saying, in sort of real terms, that each 1 second, the spin period of the Crab is about 10 to the minus 13 seconds longer than it was in the previous second. So these things don't spin down very fast. It's spinning down on a timescale of about 1,000 years. So if you put in those numbers, you get a spin down ellipticity for the Crab of about 7.6 times 10 to the minus 4. And so the Crab can't be any more non-axisymmetric than that, because if it were, it would have to be spinning down faster. In fact, we know it's actually a lot less non-axially symmetric than that, for reasons I'll come into in a moment. But it's an instructive thing to play around with this formula. There are other pulsars like the millisecond pulsars where you get much smaller spin down limits, more like 10 to the minus 8, 10 to the minus 9, 10 to the minus 10. But for these young pulsars like the Crab, you get these, this is considered a big number in the context of neutron star mountains. And can I check? I just had a warning that my internet was slightly unstable. Are you still able to hear me okay, please?
Yes, yeah.
Okay, thank you. Thanks for that. Okay, let's keep going. So you can then talk about spin down upper limits on the gravitational wave itself. Let me go back a slide to explain this. So what I'm saying is that if we can measure the period P and period derivative P dot for a pulsar, we can get an upper limit, well, from equation 15 on its ellipticity. If one then goes back to our formula, equation 8 for the gravitational wave emission, one can then translate that into a spin down upper limit on the gravitational wave emission. And that's precisely the thing that's plotted here. So there'll be a version of this plot in lots of different LIGO-Virgo papers. This is one from the most recent relevant paper. So it's the usual thing of gravitational wave frequency on the horizontal axis. It's dimensionless strain sensitivity on the vertical axis. My eyesight isn't quite good enough to read the numbers, but is that 10 to the minus 24 at the top, 10 to the minus 27 at the bottom? So these are small strains. Each little star here represents, well, sadly, a non-detection, so an upper limit on gravitational wave emission from a known pulsar, as achieved using the LIGO and Virgo detectors. So for instance, for the Crab pulsar, which is sitting over here, we're saying that, all right, LIGO and Virgo didn't see anything, so we're putting an upper limit of about 2 times 10 to the minus 26 on its emission. How interesting is that? Well, this is where the spin down limits that I just talked about are useful, because the spin down upper limit on the Crab pulsar, if you put the numbers in, is a few times 10 to the minus 24. So if all of the energy that the Crab pulsar was losing was going into gravitational waves, it would be really easily detectable. It would have been emitting at the 10 to the minus 24 level. So you can see that the actual upper limit is about 2 orders of magnitude better, i.e. smaller, than the spin down upper limit. You can put this in different ways. So this non-detection of the Crab by LIGO and Virgo, I should have put there, shows that the mountain is smaller than that. If I go back a slide, the mountain is smaller than this spin down upper limit of 7.6 times 10 to the minus 4. In fact, it's the best upper limit now is about 10 to the minus 5, which in terms of energetics corresponds to no more than 0.017% of the Crab spin down energy going into gravitational waves. So that's quite an impressive and an interesting result. No one ever really thought that 100% of this energy would be going into gravitational waves, but some smaller fraction of it was perfectly plausible. So the fact that it's been constrained to this extent is I would say it's a reasonably interesting result. This mountain actually 10 to the minus 5, as I'll come to in the later part of my talk, that's actually quite big in terms of the microphysics and the nuclear physics of neutron stars, but it's not totally insane. So all of these gray triangles that point down, these are the spin down upper limits, and there's a few tens of pulsars, mainly these young ones over here on the left, where the gravitational wave upper limits have beaten, in some cases like for the Crab and the Vela by some significant margin, have beaten the spin down upper limit. So it's in these cases where the blue stars lie below the gray triangles. These are in a sense, the most interesting results, because these are the cases where, on the basis of these energetic arguments, we had a shot at detecting anything. Sadly, we didn't, but we had a shot at detecting something. Whereas you can see there are lots of these spin down upper limits, these energy-based limits, that sadly lie quite a long way below the curve. These are stars where even though you go looking for them, because maybe these limits are wrong, but it would have been very surprising if we'd made a detection, because we really expect to have to improve the noise curve by a factor of several to start reaching some of these. These are millisecond pulsars. These are pulsars that rotate very fast with millisecond periods over here. So this was using relatively recent LIGO Virgo data. It's a 2019 paper, so I think it's 01 and 02 data, I think, that's in that paper. So 03 results will be a bit better.
And there are a couple of hand-ups.
Okay. Yeah, I'm afraid I can't see the hand. So yeah, please do keep telling me. I'm very happy to take some questions right now.
Sure. Sukanta?
Hi, okay, my internet is unstable, so we'll move on if I stop talking. But are you, in your energy balance equation, am I right that you're assuming that the ellipticity itself is not varying with time?
Yeah, that's right. So if it were varying in time, then for a start, this integration here wouldn't be so straightforward, because whatever time dependence is in the ellipticity in equation 10 would make itself felt in the integration. But yeah, so basically in all of this, the ellipticity is assumed constant. For a mature star, that may be a good approximation. We don't really know, because maybe they're not evolving fast. If a star is born spinning really fast though, and is emitting strong gravitational waves, as the star spins down, its sort of rotational bulge, which isn't something I've talked about so far, will decrease and the crust will crack. And it's perfectly plausible that that could actually change this sort of ellipticity. So it is quite a strong assumption, actually, that this ellipticity is constant.
Thanks.
Thanks. Aditya?
So my question is about how you're assuming this value of IZZ to be 10 raised to 45, but from what I know, not all pulsars have very good mass measurements and so on, right? So is this? I mean, so then I would imagine that there would be some sort of degeneracy between IZZ, the measurement of IZZ and epsilon. Is that right?
That's exactly right. I've simplified the story a bit by always putting 10 to the 45 in here, but maybe to make this point, if I go back to equation 8, the thing that is actually measured by H naught isn't epsilon, it's IZZ times epsilon, which from equation 7 is IYY minus IXX. So that's the thing that you'd actually extract, except that also is divided by R. We don't know the distance separately. So I'm afraid everything's tangled up. But so there is that slightly complicated degeneracy. But on the other side, you're right. I mean, we don't know the masses of neutron stars well, and worse than that, even if we knew the mass to 16 decimal places, to turn that into a moment of inertia, you'd also need to know the equation of state, and we don't know that. So in practice, there's probably something like a factor of 2 uncertainty in the moment of inertia. So maybe the bracketing it between 10 to the 45 and 2 times 10 to the 45 would be a prudent thing to do. Does that answer your question, Aditya?
Yeah, so just one small question. So then when you do such kind of searches from LIGO Virgo data, what kind of masses do you assume there? Or do you just assume, I mean, is just assume that they have some fiducial equation of state or something?
Yeah, so generally, if we need to present results using a moment of inertia, we'll put in, I think we normally put in a 10 to the 45 value. I think we've done some things where we maybe give brackets, but we don't invest too much energy on it, because A, we've not made detections, and B, as I say, there's a degeneracy with the distance anyway. But so we'd assume a canonical value of about 10 to the 45, and one would have to then just rescale the actual IYY minus IXX depending on that factor of 2 or so uncertainty.
I see. So this degeneracy with distance for known pulsars isn't the value boiled down to one single value or something?
Yeah, again, there is error bars on it though. So lots of pulsars, there are distance measurements from the radio pulsar data, from the so-called dispersion, which itself depends on having a model the free electron density in the galaxy. So yeah, distances are known in those cases, but again, they've got error bars that might be tens of percents, I think, from memory.
Okay, thank you. Thanks.
Thanks, Aditya. Apratim has a hand up.
Hi again. Sorry, I might have missed this. So in this particular diagram, yeah, I see the Vela pulsars and some other pulsars plotted above the noise PSD. So if why, like, if we're doing a targeted search, why are we not observing this continuous wave from these pulsars? Or am I interpreting it wrong?
No, well, the answer is simply that the assumption that's gone into those gray triangles, these spin-down upper limits, is that all of the kinetic energy that's being lost is going into gravitational waves. And so the conclusion that we can draw, and so, I mean, if we talk about the numbers specific to the crab that I've got here, it seems that for the crab, no more than 0.017% of the spin-down energy is going into gravitational waves. And if it so happens that the crab has actually got an ellipticity of, I don't know, 10 to the minus 12 or something, you know, some tiny fraction of its energy is coming out in gravitational waves. And we know, right, that the crab emits a lot of electromagnetic energy because it's powering its nebula. You know, it's got a strong rotating magnetic dipole. It's got a surface magnetic field of about 10 to the 12 Gauss. So we know that the crab has to be emitting quite a lot of electromagnetic energy. So the fact that we're not seeing these gravitational waves is just sort of confirming that, yeah, okay, a lot of this energy is coming out in the electromagnetic channel.
Thanks. Yeah, got it.
All right. Are there any more questions, or shall I carry on with the slides?
You can carry on, Jan.
Okay, thanks. But by all means, do keep asking. But as I say, I can't see the hands go up, so just do let me know when you need to. All right. So we think about these sorts of searches for known pulsars a lot, generally isolated ones, but it's worth talking about gravitational waves from recruiting neutron stars too. This picture is just an artist's impression, rather an old one now, of an accretion disk around a neutron star. So this idea is there's a neutron star sitting at this disk. It's in a binary, and the accretion disk is being fed by some low mass companion. Accretion is where we think pulsars get spun up to millisecond periods. So these millisecond pulsars, these stars that were on the right of this slide, you know, frequencies of hundreds of hertz, we think that these were very, very slow pulsars that were accreting systems, and because they were fed by this accretion disk, that carried a lot of angular momentum onto the star and spun them up. So that's a good thing, right? High spin frequencies are good if you're talking about gravitational wave emission. And it means that for these sorts of systems, while they're accreting, there'll actually be a spin-up torque. And so it's even possible that the star might come to some high spin frequency equilibrium where there's a spin-up torque from accretion and there's a spin-down torque from the gravitational waves. And in fact, one can play a game. You should think of it now as a torque argument rather than an energy argument. Equation 17 is balancing the spin-up torque that you get from accretion, that's the thing on the left, against the spin-down torque from gravitational waves on the right. So on the left, m dot is the mass accretion rate. You know, so maybe it's like, I don't know, 10 to the minus 9 solar masses a year. This thing in the brackets, 2mr to the half, that's just the angular momentum per unit mass that you can easily calculate, like using Newtonian gravity. It's basically just the consequence of Kepler's laws. It's the angular momentum per unit mass of something that's in an accretion disk. When we imagine that it detaches from the disk and falls onto the surface of the star at some accretion radius, r accretion as I'm calling it. So this is the rate at which angular momentum is being gained by the star. This right-hand side is just the gravitational wave luminosity divided by omega. That turns it into a torque. And so one could use this formula and rearrange this in terms of epsilon to get some estimate of how big the mountain would be in the case of this torque balance applying. M dot is something that astronomers can estimate because if, the X-ray flux from these systems is basically proportional to the accretion rate. So you can have some simple model where you can translate the observed X-ray luminosity into an accretion rate. And that's where these numbers of like 10 to the minus 9 solar masses per year come from these sorts of observations. And so you could get some, well, you could call them estimates, probably better to call them upper bounds on gravitational wave emission from these systems. It's perfectly possible, sadly, that equation 17 doesn't apply at all in these systems, and it could be that they come to some sort of spin equilibrium that's got nothing to do with gravitational wave emission and rather is to do with something relatively boring, right? The interaction of the star's magnetic field with the accretion disk. So one doesn't necessarily absolutely require gravitational wave emission in these systems, but it could be there. And I'll say more about this when I talk about armoids at the end, probably. But well, no. Let me just say one interesting thing now. So when you look at the spin, so we do measure the spin frequencies of some neutron stars in these accreting systems, and they are quite high. Lots of them are between about 300 hertz and 600 hertz. So those are high spin frequencies, but we're not sure why they're not much higher. In principle, this accretion torque that's on the left of this equation, if it wasn't balancing anything, could spin these neutron stars up pretty well to their Keplerian breakup angular velocities. So the angular velocities at which the star would be rotating so fast, it would start losing mass at its equator. And we don't know exactly what those spin frequencies are, but that's more like a kilohertz or maybe 1.5 kilohertz. They're not spinning that fast. And no one's completely sure why. It may not have anything to do with gravitational waves, but because there's quite a strong scaling with spin frequency in equation 17, this goes as omega to the 5th, right? If you combine those powers. One explanation that's been put forward, and one version of it's in this Bildston paper that I've referenced here, is that maybe all of these stars have got little mountains on them, and that when the star spins fast enough, because of this strong scaling of the gravitational wave spin down torque with omega, once you reach a frequency somewhere in the region of 300 to 600 hertz, you get this balance of equation 17. So it could provide a rather natural way of explaining why you don't get spun up to kilohertz frequencies and why we don't see radio pulsars spinning faster than 716 hertz. So maybe it's wishful thinking, but maybe it's really what's going on in nature. But we've not seen these sorts of gravitational wave signals yet, so we don't really know. So those are the sorts of upper limits that one can make in systems where we've got a lot of electromagnetic information, and we know how their spin frequency, and in the case of isolated stars, the way in which the spin frequency is evolving. The next question is, what can we do in the case of the so-called indirect searches? So we're just looking like a supernova remnant or a globular cluster or something. What can we say in terms of energy-based arguments as to how strong those sorts of signals might be? So it's not quite as easy, but one can still say something. What we can do, in fact, let me go back and show you equations 8 and 11, because we're going to make use of those now. So equation 8 that we wrote down was simply the gravitational wave amplitude. It was something that went as omega squared times epsilon times 1 over the distance. And equation 11 was this solution that we got if we assume that we had a star that was born spinning at angular frequency omega naught, and at time t, it would have a smaller angular frequency omega t. So if you combine those two equations, you get equation 18. So it tells you how your gravitational wave amplitude monotonically decreases as the star ages. So equation 18 can be approximated if we again make this assumption that our star has spun down a lot since birth, which in other words means that the time t now is much bigger than this tau, and use the definition of tau, you find an even neater sort of cancellation than the one we've talked about before. If you make this assumption, you get equation 19. if you look at equation 19, so this is an estimate of how strong the gravitational waves would be today at time t for a star at some distance r. And this t you can think of as the age, right? So if t equals 0 is the time when the star's born, like in a supernova, say, then this is its age. The dependence on omega naught is gone. So this doesn't depend on how rapidly the star was spinning at birth. But bear in mind, though, it has to have been one spinning fast enough for this assumption of it having spun down a lot to apply. And epsilon has dropped out, which is perhaps even more surprising. So this is independent of the ellipticity. It's as if we don't really care what the ellipticity was, because stars maybe that had bigger ellipticities, well, bigger ellipticity buys you a stronger gravitational wave emission, but it makes the star spin down more. And that's the cancellation that's going on here, and why the ellipticity has dropped out. So what this means is, in practice, if you've got an estimate of the distance to your, say, supernova remnant, and you've got some estimate of when that supernova took place, you know what the age is of the neutron star, you can use this formula to give an upper limit and how strong the emission might be. And I say upper limit because, again, we're making this very strong assumption that all of the energy loss is through the gravitational wave channel, which in practice, it probably won't be, right? So here's an example from a very recent LIGO-Virgo paper of doing precisely this. So this was a paper that looked at gravitational wave emission from 15 different supernova remnants. If you look at this left-hand plot here, it's a plot of the gravitational wave frequency against gravitational wave amplitude. Again, no detections were made. So this is the upper limits that were placed. There's actually, well, there's a few curves here, but if I just, so the LIGO and Virgo results are presented separately. But anyway, the point is that we've got upper limits then that are as strong as about 10 to the minus 25 in the gravitational wave amplitude at round about 200 hertz. Those are the best results there. This completely horizontal pink line here is the age-based limits. It is the what you get if you take the known. So I haven't told you what so this is called, if I go back, this is called the Vela Junior supernova remnant. That's its proper name there, G266.2. If you put in the estimated distance to this and its age, because there is an age estimate available, you get a particular H0 energy-based upper limit, and it's this thing here. So this is telling us that these LIGO-Virgo results are interesting. They're beating by, I'm reading it off by nearly 2 orders of magnitude, the energy-based upper limit. So again, it's sad we didn't detect anything, but it's saying that in terms of the energetics, at least, there would have been a chance of detecting something. If instead you look at the right-hand plot, then so now again we've got gravitational wave frequency on the horizontal axis, but now rather than presenting the upper limit on H0, the gravitational wave amplitude, this is the upper limit on the ellipticity. 3 different supernova remnants are shown here. Just look at the green curve, so the lowest curve here. This is the one for Vela Junior. Whereas the energy-based upper limit, sorry, I'm getting ahead of myself. So this is telling us at a given gravitational wave frequency what the upper limit on epsilon was. So for instance, if it were the case that Vela Junior was today spinning at 200 hertz, then we could say that it's, assuming it's had a constant ellipticity all its life, the thing that Sukanta asked about, so quite a strong assumption, but assuming that, then its ellipticity is no bigger than a few times 10 to the minus 7, which is small enough that it's not a crazy result. And at higher unknown spin frequency, you could even have ellipticities of 10 to the minus 7. So we're beginning to constrain the ellipticity quite tightly here, no bigger than a few times 10 to the minus 7, which is a neat result. And the corresponding energy-based upper limit on epsilon isn't shown here, but it would be some sort of curve here. It's flat in the left plot, but a function of frequency in the right plot. Okay, so again, the point of these energy-based upper limits is it's telling us when we had a shot about seeing something and telling us that, yes, the LIGO and Virgo results have for the last few years been interesting in this regard because they're beating, for some of these supernova remnants, the energy-based limit. Vela Junior is the best one. That's why I've shown you that. It's the best in terms of beating this limit. Let's now talk about all-sky searches and what one can do in terms of energy-based limits for these. So now the name of the game is rather different. In these so-called blind all-sky searches, we're not assuming any particular knowledge about the spin frequency of the source. But what I'm going to do is sketch out an argument where nevertheless one can make some sort of estimate of how strong the strongest signal might be. The idea is that we're going to imagine that there exists some unseen population of neutron stars, all of which were born spinning fast and have since spun down only through gravitational wave emission. Cristiano Palomba coined the phrase gravitar to describe this. So some people call these gravitars. And the argument I'm going to sketch out now is actually given in Kip Thorne's article in 300 Years of Gravitation. It's an argument attributed to Roger Blanford, and it's rather ingenious. And the model goes like this. What we're going to do is we're going to model the galaxy as a flat disk of radius RG, G for galaxy. We're going to assume that a neutron star, or gravitar, is born every delta t years. So maybe that's like 100 years. And that's a plausible birth interval, comparable to the supernova rate. And if we do that, then we can let n denote the number of stars with HT or less. So then n is big T over delta T. So if you wanted, say, to know how many stars, how many gravitars there are in the galaxy with an age of 10 to the 4 years or less, well, it'd be 10 to the 4 over 10 to the 2. There'd be about 100 such stars, whereas there'd be more older stars. It's capturing that idea. And what we can then do is say, well, we've got if we can imagine spreading these stars out uniformly over our galactic disk. So the distance between these stars, or if you like, the area attributed to each star, d squared, will be the area of our galaxy, pi rg squared over n. So we're just dividing the total area of our galactic disk up into n little patches. And so if we take the square root of that, we've got an estimate of the distance between these n stars. And what we can then do is we can go back and we can eliminate n in terms of t. So then we get equation 22. The way to interpret equation 22 is it's the distance to the nearest star of age t or less. Okay, that's the way to think of this. And what we can then do, so it's quite a devious argument, we can then take this equation for d and substitute it back into our equation. So it's equation 19 for our gravitational wave amplitude as a function of time, assuming that stars are spun down a lot. And if you do that, you get equation 23. And this is for a star of age t. And so if we identify the time now with the age of our oldest star in our set, you get equation 24. And if you look at equation 24, it's a very neat looking result. Why? Because we've not had, it doesn't contain the birth frequency of this population of gravitars. It doesn't contain the ellipticity, which is just as well, because we don't know either of those two things. It's built out of known quantities like the moment of inertia and the galactic radius, and then this delta t that we said is ballpark 100 years. And so in fact, we've had to make some very strong assumptions to get equation 24, but having obtained it, it's just got stuff that we know in. So this was basically Blanford's argument. It sharpened up a little and refined in an old LIGO Virgo paper from 2007. But basically, if you put the numbers in, then you get so I parameterize not in terms of 100 years, but 30 years in this formula. So that's maybe a little optimistic, but you get a gravitational wave amplitude of a few times 10 to the minus 24. So that's in the argument. Actually, so people, Nipsel and Allen, have looked at this argument a little more carefully since. And when you actually look at the details, it doesn't work out quite as neatly as this, because implicit in the argument that I've just given is that there's been enough time to reach a sort of a steady state for these sort of statistical arguments to apply. But what's likely to be the case is that unless stars are born spinning really fast with big ellipticities, they won't have achieved this steady state. And this formula for the number of stars of HTLS, well, no, that one's all right. But basically, the population wouldn't yet have evolved into a steady state. And basically, they found the actual result by simulating a sort of a hypothetical population scattered all over the galaxy, and was about an order of magnitude smaller than this. All right, so it's not a totally useless argument, but it's not completely accurate. And also the flat disk assumption wasn't a great one, because for nearby stars, they're spread out in a more like a spherical way. But anyway, it's the best you can do with a simple energetic argument. This is an example of at least recent LIGO Virgo all-sky search. So it's gravitational wave frequency on the horizontal axis against strain amplitude. You can see the sorts of numbers. The best results are a bit better than 10 to the minus 25. So the Blandford result was a few times 10 to the minus 24. So that's been beaten comprehensively. And things have pushed about more than an order of magnitude below that. So again, I would say on this basis, on this energy basis, these results are beginning to get interesting. These are all upper limits, right? You know, no detections, but they're beginning to get interesting. These different curves correspond to slightly different searches, and some of them are O2, some of them are O3 data. But these are very difficult searches to do because of their computational expense. I think we're getting close to the point where we were going to stop. Logically, this would be a good place for me to stop, because I'm about to sort of move on to a different topic. So let me ask, would you be happy for me to stop now and pick up again then in our next session?
Yes, Jan. So you can continue with lecture for in the next half, and then we can move on to the tutorial at 4 p.m. Sorry. Yeah.
All right. And if anybody wants to ask anything now on anything I've said so far, that would be fine as well.
Yeah, I had slightly out of the box question. So for accreting systems, you mentioned for neutron stars, we can have, because of the accretion, continuous gravitational waves. But I was wondering, for black holes also, can we have waves in that regard? I understand that we expect them to be spherical, like not no ellipticity would be there, but still would the accretion lead
Well, I mean,
to...
certainly the black holes accrete, and you know, Cygnus X1 famously was like, you know, the early black hole candidate that was identified because it was accreting strongly. But I don't think there's any sort of real analog of this sort of emission in the black hole case. I mean, I think they just remain very close to axisymmetric and just swallow up the stuff, and there's no, you know, there's no asymmetry connected with it. So I don't think you can get that sort of emission. I mean, people have talked about boson cloud emission, but that's not intimately connected with accretion. Then you don't need an accretion disk for that to work. Does that answer your question?
Right. Yeah. Yes. Yeah. Thanks. Apratim has a question.
Yeah. Thanks, Ian, for the talk. So I have a couple of questions. One is related to the like the initial slide where you said that you're not going to talk about the other sources. Can you like say briefly about whether these sources are more promising and why, or is it just a difference in the modeling from the neutron stars, the rotating neutron stars that you talked about? And the second question is, I'm not sure about this, but how, like observations from the observation of pulsars in radio frequencies, how do they help in any way detecting gravitational waves apart from like the targeted searches that you do? Like, is there any other way that you get help from radio astronomy?
Okay, no, I understand. So the first question, I mean, how promising are these more exotic mechanisms? So I've got to preface this that I'm not really an expert on these other things. It's neutron stars I know about. My own personal opinion is that certainly the boson clouds and the dark fun and dark matter are very speculative, and I would have quite low confidence in us seeing anything. I suspect that some of my continuous wave colleagues might disagree, particularly those that invest more time in it. But I'd say they're speculative. Of course, it could mean, because we know so little about them, it could mean that they are, they could be even stronger than people think, I guess. But I would say they seem somewhat long shots to me. And I say that in part because even though I said that neutron stars are well understood, they're relatively well understood. And we know, that they have got solid crusts. We know that they are threaded by strong magnetic fields. And we do know that rotating stars, if perturbed, oscillate. So it was, in a sense, very confident about the ingredients there. We're not even sure if some of these particles truly exist in nature, for the boson clouds and the dark photon, dark matter. They might not be realized at all. Primordial black hole binaries, I'd probably place somewhere in the middle in terms of plausibility, because, all right, we don't know what the spectrum is of primordial black holes, but we certainly know that black holes exist, and it doesn't seem too much of a stretch to imagine that they were produced. And I mean, people do try and model these things, right, in the early universe, and they do predict that they can be formed in significant numbers, and indeed in binaries. There has been some modeling of that. So I would put, if I was placing bets, I'd put most of my money on the neutron stars and only a little on the others. But I would put some on the others. So in terms of your second question, then, in terms of the usefulness of radio pulsar astronomy beyond, so for targeted searches, it's useful because it tells you the spin frequency and how that's evolving. Another thing that you can get from electromagnetic observations is some information on the orientation of the spin axis of a star, if there's some sort of ring structure around it that's been seen in X-rays often, I think. So that can help constrain the geometry. In terms of other constraints, well, for the targeted searches, just having a sky location is useful, like where the supernova remnant is. And some of those supernova remnants, even though we don't see a neutron star, like the Cassay one, we see a glowing hotspot. So having an exact sky location for that makes it a single sky template search. What else? What other use can you make of electromagnetic observations? Helping to pin down binary parameters for those systems in binaries helps. But that's just a variation on the timing problem. Is there anything else that we get from the electromagnetic observations? So it's not from radio pulsars, but having estimates of the ages and distances to supernova remnants is useful because it enables us to work out which are the best bets. And so we can target more of our computational resources on them, because basically the younger ones and the closer ones are better bets. I'm sure there are others, but I can't think of anything else off the top of my head.
Sure, thanks. No, I was just wondering because you have this constraints on the equation of states, which uses multi-messenger astronomy. So I was just wondering whether the same, in a way, this applies even for continuous wave observations. But thanks, Ian.
It's okay.
Aditya also has a hand up.
Yeah, I thank Ian for the talk. My question is, so this electricity parameter, is it dependent on the equation of state? Is there so given an equation of state and let's say a mass, are there theories that predict what the typical values of these electricities are?
So it's this sort of thing I'm going to talk about in the next part of my lecture. Basically, how big epsilon will be limited by there's something to do with the equation of state. In particular, it will have something to do with the breaking strain and shear modulus of the crust. But if you can also have mountains that are supported by magnetic fields rather than elasticity, and then equation of state matters for, how is the superconductor arranged? That's something that depends on the microphysics. But that's just in terms of setting maximum ellipticities, where the equation of state is important. What we don't know is what a realistic level is. Why would there be a mountain? I'll talk about that a bit in my second lecture, but that's a very difficult question to answer, and we've not really had that many ideas as to how to answer it.
Yes, so thank you.
Thanks, Jan. There are no more hand-ups. I just have one more question. So when we talk about BNS mergers, binary neutron star mergers, and let's say if the remnant is a neutron star, so then can we expect it to have non-zero ellipticity and produce continuous gravitational waves, the remnant?
So it's perfectly possible, but we don't know, but it's perfectly possible. And certainly the star's spinning fast, so that's a good thing. People have done what they call transient searches, so sort of short continuous wave searches following GW 170817. Of course, didn't see anything, and it didn't expect to because it's 40 megaparsecs is too far. But in principle, you could. So, for instance, if there's a strong magnetic field in the remnant, maybe that got wound up in the merger, that could support a significant ellipticity. You probably won't have a crust then because it's too young and hot. But you could get a bar mode instability. You could get an R mode instability. These are all things that were talked about and looked for. Yeah, so the answer is yes, it's perfectly plausible that you could. And it was searched for, but not found. And it wasn't really expected to be found because of the distance following GW 170817.
I see. Thanks a lot. There are no more hand-ups, I guess. So thank you very much.